So in this video, we are talking about exponential models. Now, this word models has come up a lot in previous videos. So when we talked about our linear models, in our simultaneous linear equations, as well as in other topics, anytime we mention modeling, it means we are trying to represent a practical situation and describe it mathematically. So in this case, we are taking practical situations, but using an exponential function. Now, the quantity usually experiences fast growth or decay. So for exponential models, we have two types. One is exponential growth, where something increases rapidly according to some function, y equals a to the power of x. That's our general exponential, where a is greater than 1. Or it will experience exponential decay. So this is when something decreases rapidly according to this particular function, where a is greater than 1. Now, just for like a general example to get you thinking about this, one real-world example where exponential models come in is to show the spread of a virus. Now, we went through a virus a few years ago. In order to sort of understand an exponential model, we're going to think about this in terms of people. Now, the first person who gets a virus, they call them like patient zero, right? So on day 0, before the virus starts to spread, one person is infected. Now, the reason this was kind of so scary as it was happening is because something spreads very fast. What they would sort of tell us was, well, one person has it, then on day 1, they infect another person. So this one person infects one other person. So now 2 people are infected. On day 2, though, these 2 people go out not realizing they're sick, and they go and infect 2 more people. All of a sudden, we have 4 people infected. Day 3 comes along. These 4 people, they go ahead and they infect another 4 people. And all of a sudden, in 3 days, we've gone from 1 person having it to 8 people having it. And because if you look at the relationship, we are doubling every single time. So this doubled. To get from 2 to 4, we doubled. To get from 4 to 8, we doubled. So if we continue doubling, we're going to get more and more and more people sick. So from these 8, it'll go to 16, then to 32, then to 64, then to 128. And all of a sudden, a week's passed and we have hundreds of people infected. So if we wanted to model something like this, we would consider, well, let's think about this in terms of days. So let's do T for time and N for the number of people infected. Now, on day 0, 1 person got infected. The first day the virus began to spread, 2 people were infected. Second day, 4 people. Third day, 8 people. Okay? Now, if we graph something like this up, let's have our vertical axis being the number of people infected, and we'll have our x-axis being the time. Now, with exponential models, we are representing a practical situation. So there's no need to draw up our entire Cartesian plane. We can't have negative days and we can't have negative number of people. So we are just dealing in this positive quadrant. So we have N, we have T. We go here from 0 and we have 1, 2, 3, 4. And let's go up. Oh, actually, let's just do this. Let's assume each grid marking is just 1 unit. Now, on day 0, 1 person is infected. On day 1, 2 people. On day 2, 4 people. 1, 2, 3, 4. On day 3, 8 people. 1, 2, 3, 4, 5, 6, 7, 8. So I can see I have an exponential that I'm dealing with. My curve starts here and it rises rapidly until we get to here. Now this will continue up. And what we actually have here is we have something that's, let's say n. Now n here is just my y. We have a to the power of t. Now this thing is doubling, okay? So the actual rule here is, because the base number just tells us at what rate the thing is increasing. It's doubling every time. So the rule we actually have here, we've shown n equals 2 to the power of t. You can check these values in your calculator, but 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. This guy over here is our rule for the exponential we've just drawn. It's a rule that models some kind of exponential growth. This is just an initial kind of early example to get you thinking about this, but we are basically describing a practical scenario mathematically and graphically. Now, in example 2, we're looking at an increase in fish population here. Now, the question says the fish population is predicted using the formula n equals 500 times 1.5 to the power of t, where n is the number of fish and t is the time in years. So we're going to construct a table of values for t and n, and we are using the values from 0 to 4, and we're just approximating the number of fish to the nearest whole number. So when you put these into your calculator, you'll get a few decimals, just round it up to the nearest whole number. Now, you can pause this video and have a go at doing this on your own. I'm just going to write the answers in these boxes. Now, when t is 0, I get 500 times 1.5 to the power of 0, which is just 500 times 1. That will give us 500. Next one, substituting 1 in, will give you 750. Next one, if I substitute in 2, it will give you 1,125 as n. For the next one, when I substitute in 3 for t, you get 1,688. And the next one, 2,531. Okay, so I've drawn up our table of values, and next we want to draw the graph of n equals 500 times 1.5 to the power of t. So because I know I'm going up kind of pretty high, I have chosen a scale to go up 500 every single time. But drawing this up, I have when t is 0, my n is 500. When t is 1, I have 750. When t is 2, I have 1,125. It's about here. Next one, when t is 3, I have 1,688. That's going to be about here-ish. And then next one, 2,531. So that's going to be about here. So I can see once again, it's an exponential model, okay? It's going up faster and faster and faster. So joining this up, trying to draw one continuous line, passing through all my points. And here I have my graph. So this is my graph of n equals to 500 times 1.5 to the power of t. So we are doing it in the same way that we've been doing in the previous video. We're just drawing up a table of values, getting some numbers in, plotting, and joining up to get my curve. So next one, saying how many fish were present after 2 years. So question C, how many fish were present after 2 years? We can just look at our table, 1,125. Part D, It's saying how many extra fish will be present after 4 years compared to 2 years. So we have our amount at 4 years and our amount at 2 years. We want to subtract this one from this one to find out how many extra there were. So the extra equals 2531 minus 1125. That gives you 1,406 fish extra. And our final question is saying estimate the number of fish after 18 months. Now that we have a graph and some kind of model, we can use this to make predictions. So we want to, using this graph, kind of figure out roughly how many fish there will be after 18 months. Now, 18 months is 1.5 years. So we're looking at where t equals 1.5. So going from here, I find 1.5, I draw up until I hit my graph. And then I go to here. So here we get roughly, and it's just an approximation. So as long as you show that you're using your graph and drawing across and it's in the ballpark, you will get the right answer. But let's just say this is approximately, let's say, I don't know, 850 fish. So this is how we can use our exponential models. We are just representing a practical situation with an exponential graph, using it to answer questions like C and D, how many fish were present at this time, and then we can also use it to estimate. So find these little kind of in-between values. We can find out how many there were in 2.5 years, maybe even 5 years if we extended this graph further. There's a lot of predictions we can make once we have our graph. But that brings us to the end of the video. So thank you so much for watching, and I'll see you next time.